sei. E os próximos passos?
Você começou esse ano? Mostrar? Não, foi ano passado.
Já em agosto.
Mas você vai sair daqui 6 meses? Sei lá. Voltando também. Vou voltar estende mais 6 meses.
E todo mundo.
2 anos e meio. Bom, Varza. Tudo bom. O BEP de doutorado que eu entendi, que assim, você fica um ano, né? E aí estende mais um ano. Mas no doutorado é só 3, né? A bolsa padrão deve ficar por 3 anos. Né? 4 mudou. Então na prática durou 5. Exatamente.
Olá, boa tarde a todos. Tenho o prazer de introduzir o palestrante hoje, nosso plenarista, o professor Pavel Zalesski. Pavel terminou seu doutorado em Minsk, 88. Antes de vir para o Brasil, ele fez vários pós-doutorados no exterior, no Canadá, Inglaterra e Áustria. Ele está na UnB desde 98 e é professor titular permanente desde 2003. É bolsista de pequeno nível 1.
Well, I was told to speak in English actually, so I will continue in English. When I came actually to Brazil in 1998, I come to Brasilia, signed actually the contract and went immediately to School of Algebra to the south of the country, where I actually met first colleagues from University of Campinas. And since then actually I started collaboration with University of Campinas, with the mathematical department of University of Campinas, and I am frequently here, right, because here atmosphere is very friendly and very receptive, and actually up to now I have more collaboration and more papers with professors of the University of Campinas than actually with the University of Brasilia. So I'm glad to be here and give this talk during this event, and I want to start with the subject of or objective of algebraic topology. What is the main objective of algebraic topology? Given a geometric object is to find algebraic invariance of this geometric object and to determine to what extent this algebraic invariance determine actually the object. And the most famous and most popular geometric object is manifold. Right? So let's go to manifold. And the most known and popular algebraic invariant of this is the fundamental group. By one of them. So here in the first plate, actually, I wrote the questions that I just told, all right, concerning manifold. Okay. But in majority of cases, fundamental group of a manifold is infinite, and from a heuristic point of view, it would be good to have finite invariance. And therefore, the question, to what extent finite quotients of fundamental group determine manifold, right, it looks natural. And having this in view, these three persons, Caligari, Friedman, Walker, asked specific question about three manifolds, whether fundamental finite quotients of fundamental group determine manifold. And of course, it is stated this way. It was a little bit of exaggeration. Why? Because first question, before asking this, we have to ask whether fundamental group itself determines manifold. And in dimension 3, this is almost the case. The counterexample is length space, length spaces, but for length spaces the fundamental group is very small, it is finite cyclic. And therefore the question doesn't have sense anyway, because if fundamental group itself is finite, we don't have to look at finite quotients. And the second issue is the following. When you have connected sum, you can do connected sum switching orientation, and fundamental group doesn't see this, right? But this is only two issues where fundamental group doesn't determine the manifold up to homomorphism, and we're going to ignore this issue during the talk and assume up to now that fundamental group of a three manifold determines the manifold, right? Because these two issues are, as I mentioned, they easily resolved, and we just continue with this. And then we come back to the question whether finite quotients determine manifold, and if not, to what extent they determine manifold. But we can look at the question, of course, a little bit broader from point of view of group theory, because fundamental group, after all, is a group. And therefore ask whether finite quotients of a group determines, to what extent finite quotients of a group determine the group. And this is an old question in group theory. It was investigated by these people, Bamsel, Remesnik, since 60s. And when we look at this question, we see that it is not really a good question without restrictions. Why? Because there are such things as infinite simple groups. Right? Infinite simple group doesn't have finite quotients at all. It means that by looking at finite quotient, we cannot distinguish it from trivial group. And the same happens with more simple example, like abelian group, like group of rational numbers. Group of rational numbers doesn't have finite quotients at all. And therefore, from our point of view, it is not distinguished from trivial group at all. Okay, so we have to make some restrictions. And what is the restriction? What is the philosophy of the restriction? Well, let's take a group, all right, and let's look at finite quotient. If some element of the group will be trivial in every finite quotient, right, then it is not visible in any finite quotient. And therefore it should be disconsidered. Right? So what is a correct way to do? So look at all groups that are can be approximated by finite quotients. Right? And this is the definition of residual finiteness. So the group is residually finite. Here is the formal definition. But the group is residually finite if it can be approximated by finite quotients in the following sense. For every non-trivial element of a group should be a finite quotient such that where this element is also non-trivial. This is the definition of residually finite group, and then in that sense this group is can be approximated by finite quotients. And in fact, in Russian term, it is exactly this term is used. Not residually finite, but finitely approximatable. Anyway, so from now on, we're going to stay with residually finite groups. Right? How can we stay with residually finite group? Well, you take a group, you take all subgroups of finite index. Right? And then you intersect them. When you intersect them, you get something which is called residually finite cost, something that it is not visible by in any finite quotient. If you take this normal subgroup, right, and quotient it out, you get a residually finite quotient. Right? And so, for any group, we can take a residually finite quotient it out, right? And then we come to residually finite group that we can investigate. And what we quotient out is irrelevant in our equation anyway, because this score is not visible in any finite quotient anyway. Okay. So, and now I want to cite open problem of Remesnikov. Remesnikov is a Russian mathematician who recently passed away, unfortunately. But his question is open. Right? If you have a free group, the question is the following. Suppose you have a free group, and suppose you have finitely generated residually finite group, whose finite quotients are the same as quotients of free group. The question whether the group itself is free. Right? This question is very open, and I remember that in the last Congress of Mathematicians that happened in Rio de Janeiro, Alan Reed, given a talk, said that so the question he will pay Beverly of his choice on the spot. Anyway, so let's go and continue, and then the question, actually, how do we deal with our problem? So suppose we have two groups. Suppose we have two groups. Suppose they are residually finite, infinite, right? Then we should look at finite quotients. So we have infinite family here of finite quotient, infinite family here of finite quotient, right? And how do we compare these two infinite families? Well, it is not clear in principle. How do you compare infinite families? All right? But there is a method here. And what we can do is do the following. We observe that this family of finite quotients form inverse limit, inverse system. And therefore, we can look and take inverse limit. And then we come to the notion of the profinite completion. So we take inverse limit of all finite quotients. Who is not very prepared to know what is, to understand what is inverse limit, I can give another definition. You do the following. You have G, and then you have family of all finite quotients, G mod n. Right? All of them. So we can take direct product of them. I mean, infinite direct product, right? Cartesian. Take direct product. This is finite object. G mod n are all finite groups. So as a topological space, we can consider it as a discrete space with a discrete topology. And then we take infinite direct product, and then this infinite direct product has topology on it, natural topology of direct product, Cartesian product. Right? It has topology, and then since G is residually finite, you see, G is residually finite, it means that every element, right, will be non-trivial in some of the components. If it becomes non-trivial in some of the components, it means that we have embedded here. So this would be a subgroup of this, right? And then we can just take a closure of G in this direct product. So we took all finite quotients, we made the huge direct product, all of them. This has topology on it, right? And we close our group in the topology. This is exactly our profinite completion. So, and then what is important is the following, that for finitely generated groups, right, the families of finite quotients are the same if and only if the profinite completions are isomorphic. So, how did we transform the problem? First, instead of looking at infinite families, we're looking only at one object, profinite completion. Secondly, this becomes now a topological group. Our profinite completion is topological group. It is compact, totally disconnected topological group. But, and this is by definition is profinite group, because profinite group is defined as an inverse limit of finite groups. But, so we came to the other area of profinite groups. And profinite groups were studied a lot, but not because of the topology, but because profinite groups are exactly Galois groups of infinite Galois extensions. So they were studied from point of view of algebraic number theory and Galois theory. And as we all know, the inverse Galois problem is not solved yet, right? So actually, profinite groups come to this to the focus of mathematicians because of this, and until now, many examples and many very interesting questions to profinite groups, to the area of profinite groups, come actually from Galois theory and algebraic number theory. right? And since this was already studied, right? We can try to take this approach. So profiling groups nowadays are not only interesting because of Galois theory, but also because they serve as a bridge between finite group theory and infinite group theory via profiling completion. Because if you have a rigidly finite group and it embeds in profiling completion, you look at finite quotient, but in finite quotient you have finite group, you have Silov theory, and so on and so on. And therefore, in profinite group, it is inherited. So the profinite groups, they somehow the centaurus in the group theory. They at the same time they infinite and have combinatorial group theory, and on the other hand, they have features of finite groups like Silov theory, Hall theory, and so on. So the most interesting is interplay between these two things, and that's actually what we're going to explore. We're going to explore this approach via profinite completion to detect properties of the original object. So again, here example of the profinite completion. If we take integers, all right, they're just integers used to be a ring, but it is also a abelian group, therefore, right? We can make profinite completion, and then it's just direct product of rings of periodic integers. Now, of course, when we take inverse limit of finite groups, we can we call the group profinite. If all those groups are just finite P groups, so we call the group pro-P. If all these finite groups are soluble groups, then we call a group prosoluble. And the same happens with the completion. So, for example, a ring of periodic integers. That one, ring of periodic integers. Of course, it is well known for number theories, all right? A ring of periodic integers. But it is exactly pro-P completion of the ring of the group of integers, right from the point of view of profiling group. So, in some sense, we're already looking at general things. We change the question. So our question now: to what extent is G determined by its profinite completion? And I will stress again, this consideration above makes sense only for a rigidly finite group. It is exactly why, that's why we fix our rigidly finite groups. Okay, but when we change the equation to the profinite completion, we get motivation from the other side. Grothendieck. Grothendieck considered algebraic variety, and he defined algebraic fundamental group of algebraic variety. How he defined it? Well, I'm not going to write it, right? Definitely, but I will just tell it, because it is not the subject of my talk. It is just complementary motivation. So if you take algebraic variety, you have field of function associated to it. When you have field of function associated to it, you can take maximal unramified extension of it, and then you take Galois group of this maximal ramified extension, and this is by definition of Grothendieck is exactly a fundamental group of algebraic variety. So when Grothendieck defined it like this, he defined it in pure algebraic terms, right? And in fact, this definition also has sense over finite fields, where you don't have anything. But what he proved to the Poland that if you take this variety and consider it over complex numbers, then our algebraic fundamental group is exactly the profinite completion of our analytic manifold, of fundamental group of our analytic manifold. Right? So what he was interested in, if we come into our question, to what extent algebraic invariant of our algebraic curve or algebraic variety, right, determines our algebraic invariant, namely fundamental group of our complex variety, of our analytic manifold. Right? right? And that's why he was interested in, and this complementary motivation to study profinite completions. Plus, another motivation that Grothendieck found remarkably close connection between the representation theory of finitely generated groups and profinite completion of the group, but this is the subject of absolutely different direction, and we want to come to our three-manifold. So why we are in business here? Because fundamental group of three-manifold is residually finite. So whatever I told before, right, is applied here, and therefore we can ask this question. So to what extent a three-manifold M is determined by the profinite completion of the fundamental group? Right? And this motivates study of profinite completion of three-manifold. Now, when we study profinite completion of fundamental, it's a group. What does it mean to study the group? Well, we want some internal structure of the group. Right? So, and usually it is called subgroup structure. So we want to understand how subgroups behave there. Right? And we have to start with something. Right? When you go to study finite group and we start a finite group, what first you learn? Syllops theory, right? So what is coming to the game are finite P groups, right? You study whole theory, and what coming to the game are finite soluble groups. This profinite case, it is absolutely the same, right? When we study a subgroup structure, right, you can look first at pro-P subgroups and pro-soluble subgroups, right, which are inverse limit of finite P groups or finite soluble subgroups. And that's what we're going to do. Right? The most important subclass of profinite groups are pro-P and pro-soluble, like in finite group theory. And of course, in finite group theory, people look at only at finite simple groups, but for profinite group, it doesn't make sense because every simple profinite group is finite. Okay. I give a description that what here I projected just for a moment. It is a description of pro-P subgroups of the profinite completion of three-manifold obtained some time ago by Speaker and Henry Wilton. But I don't want you to study this, right, or to look at it attentively, because it doesn't matter for the talk, this description. What matters is that this description exists, because I want to use the classification of pro-P subgroups of profinite fundamental group. Not really, it is important now to know what are the groups appeared here, right? But basically what is called is free pro-P product of a list of certain group, pro-P groups, right? And what is free product I'm going to define a little bit later for all classes of groups, because it is more convenient there, right? So there is two lists of pro-P groups that give full description of pro-P subgroups of profinite completion of fundamental group. Some of them finite, some of them infinite, some of them big, some of them small, but we have a complete list. Right? What we want to concentrate here on finitely generated pro-soluble subgroups of the profinite completion of the fundamental. Right? Okay. Right. So what we are going to do, and then we come to our manifold. So suppose we're given three-manifold. First, three-manifold, it admits prime decomposition, which is called Milnor-Knežević decomposition, right? So basically, from algebraic point of view, so it admits decomposition into connected sum of this, and what it means for group theory, right? That it has the fundamental group of it has decomposition into a free product, right, of groups which are M1 and M, where fundamental group doesn't split anymore as a free product, and free group Fr here. And now what is a free product? Here the definition, right? So what do we have there? When you have talking about free product, first of all you have collection of some groups, Gi. Some collections. And then you want to build the group of the object that contains all of them, right? But put on as many internal structure on this as little as possible. So what you do by presentation. So in any category, abstract groups, profinite groups, pro-P groups, pro-soluble groups, you define free product the same way. You just take this all GIs group as generators, and then impose relations only on those which are in every GI. So here it is formal definition. So presentation, group generated, free product is generated by GI with relations which are GI, right? And I runs. That's it. This is a free product in any category of group, right? It has universal property that one needs at certain. This is the simplest definition we can imagine. Okay? And from geometric point of view, presentation is something which is given actually by geometry. Okay, so this is definition, and then one can see that suddenly we have to first deal with the free product. First thing. All right. And this is the first theorem that we have to go through. Again, it is proved jointly with Henry Wilton that prime decomposition can be detected by finite quotients of fundamental. Right? I mean, profinite completion recognize decomposition in irreducible manifolds, in prime manifolds, irreducible manifolds, and actually it also detects, profinite completion detects this geometric property that M is irreducible, right? M is irreducible if every n-1 sphere contains a ball. Right? So it's purely geometric property, but it is detected by finite quotients of our fundamental group, or in the other words, by profinite completion. So when we have it, right, we want to reduce our consideration somehow to the free factors, to irreducible three manifolds. And what we have to do, we have to do describe pro-soluble subgroups of free profiling product. And that's what I did, but I'm going to use it not just once, but as an induction engine. I'm going to use it several times later. And the theorem is basically what is, right, that if we have free profinite product and we have pro-soluble finitely generated subgroup, then one of the following happens. Either it is free pro-soluble product of HIs, and each HI is finitely generated pro-P group, right? Or it is very small profinite group, which is called Frobenius profinite group. In this case, Z pi, right, is pro-cyclic group. It is inverse limit of cyclic group, and C is finite cyclic group. Right? The co-prime order is this co-prime action and so on. It's Frobenius profinite group. And the third case, it is H is a subgroup of some free factor, and therefore you cannot tell anything about this because it depends on Gx, which should be given. Right? You cannot tell anything, right? But it is, but then it produces reduction. So let's interpret this theorem for our three manifold, for our prime decomposition. So we have n, which is connected sum of our manifolds, all right, invisible, and we have a finitely generated pro-soluble subgroup H of our fundamental group, and here is, something is missing here, namely head is missing here. You see, this should be head. This is profinite completion. Alright? And then one of the following group. First, it will be a subgroup of free pro-soluble product of HIs, where H is finitely generated pro-P group, which is isomorphic, right? Isomorphic to a subgroup of some pi1 of Mi. Okay? But for P subgroups, right? For finite unit for P subgroup of three manifolds, I already described this in my theorem with Henry Wilke. So I can apply it here, and therefore I finish here the first case. So those HIs are described, and here we have HIs, and then we have reproduced. So right. Second case, again, this small group which is Frobenius groups appear, and this we have nothing to here to investigate, because it is a very small group and it is very well understood. Right? And then we come to the third case where H is isomorphic to a free factor pi1 of Mi, but this guy, right, Mi, now irreducible manifold. Right? So we reduced our problem to irreducible manifold. Okay? Now we have to understand what are prosoluble subgroups of profinite completion of the fundamental group of irreducible. Okay, let's go further. So now we have a reducible manifold, and now there is a big difference between two-dimensional and three-dimensional case. In two-dimensional case, the manifold is a surface, all right? And surface admits always three geometries by uniformization theory, either Euclidean or spherical or hyperbolic. Now, in three-dimensional case, it is not the case. What we need instead is three manifold can be cut along the torus in pieces, and each of these pieces admits one of the so-called 8 Thurston geometries. Right? And this way of cutting the surface is called JSJ decomposition. Right? And of course it is reflection of the fundamental group, but I'm going to now to list the 8th Thurston geometry, where I actually order them by the increase of the fundamental group. So the first case is spherical geometry. It is when fundamental group is 5. Right? The second case is the geometry as 2 times R, where in this case fundamental group is virtually cyclic but not finite. When I say virtually, it means I'm having subgroup of finite index with this property. So virtually something means having subgroup of finite index of with this property something, right? And from geometric point of view, it is the same as to have finite covering with this property, right? So it is always, it is very typical in geometry to have this virtually. Right? Now, third case, Euclidean geometry, when fundamental group is virtually abelian but not virtually cyclic. Then we have new geometry, where fundamental group is virtually nilpotent but not virtually abelian. Right? You see, increasing. Then sol geometry, where fundamental group is virtually soluble but not virtually nilpotent. And then we have 3-big geometry. 3-big geometry is the following. Then geometry H2 times R. H2 is upper half hyperbolic plane. Fundamental group is virtually Z times fundamental group of Riemann surface. All right? S is closed Riemann surface. Now we have this case where this fundamental group doesn't split as a direct product, right? Non-split expansion of this. Z by fundamental group of S. And then hyperbolic geometry, that is the most complicated case, where fundamental group doesn't contain direct product of Z and Z. Direct product of Z. And I showed, right? I showed that this is geometrization conjecture, but this geometrization conjecture follows from solution of Poincaré conjecture, which was solved by Perelman. So actually, the truth of this follows from resolution of Poincaré conjecture by Grigori Perelman. Okay, so we have do this, and then the question is the following: how by profinite completion of fundamental group of 3 manifold, right? All right, or looking at finite portion of this, we can recognize this JSJ decomposition. Right? So this decomposition by cutting this in pieces which have geometric structure is called JSJ decomposition. First thing we need to recognize it. We have to look at our profiling completion and see this, detect this JSJ decomposition. And this is detectable, and which is another theorem of speaker with Wilton. And plus, right, if the fundamental group already geometric, or sorry, if the manifold is already geometric, already has geometry, right, our profiling completion detects actually which geometry is, right, detects the geometry. This is the second theorem of Henry Wilton and mine. So we are in business. We can try to reduce our question to geometric cases, but how? So when we have closed irreducible, orientable irreducible manifold, we have JSJ decomposition, and then fundamental group of this acts on a tree. In this, we come into the famous Basser theory of groups act on a tree. So fundamental group of this acts on a tree where vertex stabilizers are exactly fundamental groups of geometric manifolds. And edge stabilizers of the tree are just torus, fundamental free abelian groups. Free abelian groups. The fundamental group of torus. Right? And moreover, this action is for acylindrical. What does it mean? It means that every non-trivial element cannot fix more than 4 consecutive edges. Right? Right? If something fixes more than 4 consecutive edges, the element, this substance should be trivial element. This property is very important now in geometric group theory, acylindricity of the action. And the problem is that we need somehow to have something like this in the for profiling completion. Fine. And here it is. Profiling JSJ decomposition suffice after the profiling completion. This is another theorem of the speaker and Henry Wilton. And therefore we can use profiled version of Basser theory of group acting on trees developed by Melnikov, Ribas and Speaker during the years. But what is more important, that applying this one obtains 4 cylindrical action in the profiling case. Right? And that's what helps. Because when we have this acylindrical action, right, we have this theorem obtained by my student Lucas Lopez and Speaker, that in this case we can embed our pro-soluble subgroup of a group G that acts acylindrically, on profiling simply connected graph, into a free profiling product. And now we can apply induction engine. You remember that I had a theorem about pro-soluble subgroup of free profiling products, so here I can apply it now, again, right? And I get as a corollary what? I get to the corollary that again, H is pro-soluble subgroup, and therefore it is a subgroup of free pro-soluble product where Hi are exactly again pro-P subgroups, and therefore we can again apply classification of finally generate pro-P subgroups of 3 manifolds that was mentioned before as the first theorem. Or we have this Frobenius group, or H is a subgroup of profiling completion of geometric manifolds now. So we reduced all the equation to geometric manifolds. So now what we have to do? We have to study all these 8 geometries, right? Apply our question to each of them. Okay, coming to geometric manifold, which one is the most difficult? It is hyperbolic one. So if we have closed hyperbolic manifold, then we have fundamental group of it, right? Remember, we don't have Z cross Z, right? Then the theorem, again obtained with together with my student Lucas Lopez, says that soluble subgroup of the profinite completion in this case is projective. What means projective? Well, the point is the following: when you have in abstract case and in Pro-P case, when you have free group, then subgroup of any free group is again free. That is famous Schreier's theorem. However, in profinite group, for profinite case, it is not true. All right, the group is called projective, namely projective group. All right, is the group of cohomological dimension 1 in the profinite projective group G. Projective group is the same as profinite group of cohomological dimension 1. Right? But it calls projective because it has the same property as projective model. Who studied commutative algebra a little bit knows what is a projective model. Projective model has the following property: if you have epimorphism to the projective model, right, then it always splits, right? And therefore, projective model is a direct summand of free model. For profinite group, it is absolutely the same too. Any epimorphism to projective group, right, splits, right? And therefore, any projective group is a semi-direct factor of a free profinite group. So one can take it as characterization, but this shows that actually this H is basically, there is not too much say more about this H, because if you say that it's projective, you already say a lot about this. Right? And the rest of geometries we have to do case by case. And I'm coming to the last theorem. All right, where I give a characterization of all prosoluble groups of the profinite completion of three manifold. And again, like in for Pro-P case, it is not important for non-specialized whatever what are the lists. We can look it up and so on. When you start to study it and you need it for something, you look at the list. Important that this characterization is obtained. So we have characterization of three prosoluble subgroups of the profinite completion of fundamental groups. So it is isomorphic to free prosoluble product of Pro-P groups listed at the very beginning in the theorem of Henry Wilton about Pro-P groups, or it is Frobenius group, or it is a finite group, which is well understood. It is dihedral central extension either of dihedral group, of tetrahedral group, or octahedral group by a cyclic group of even order, right? Or you have profinite completion of three-dimensional Bibi-Brach group. Then you have two cases of this metacyclic group, Z, no metacyclic, meta-abelian group, Z squared by Z. You have this one, which is also meta-abelian. All right, and finally, there's a possibility of finite an extension of torsion-free procyclic group, right, by a subgroup, prosoluble subgroup of free prosoluble product of finite cyclic P group. This group comes from the surface, so it is actually from surface manifold case, right? And this what the principal theorem I wanted to say, and I think it is a good point to stop, since I already overloaded audience with information.
So you're welcome to ask questions. Okay, if there are no questions, I can ask one. There are many results about three manifolds, but what about four manifolds? I think it should be much more complicated.
Yeah, first it is complicated because any finitely presented group is a four manifold. to restrict a lot, right? And then if you do your restriction, there are much more geometries, much more complication. But there is one paper of one Chinese professor who wrote something about this, right? And one can find it in the archive at least, right, about this. But when I talked to Henry Wilton, he told that he looked at it and he saw that this paper is basically reduces to the cases where it is done, you can do something like with the three manifold the same way, but there is nothing new, basically, conceptually there.
I believe Jonathan Hillman has a book about four manifolds.
Yeah, he has a book, but not he doesn't deal with these questions. He doesn't deal with these questions.
Okay. If there are no other questions, we can thank the speaker.